So I would like to thank the organizers for inviting me here. It's my first time in Boston, so I'm pretty happy about that. I'm going to talk about this slightly older paper that I wrote with Francesco Benini and Lorenzo Di Pietro some years ago, because it was kind of well aligned with the workshop, I think. And I also prepared like a shorter talk because I knew it was the last one and everyone is tired. I'm also very tired. So in the interest, of my resilience, I think I tried to make like half an hour talk. So let's see if I succeed in this. So this talk is about a toy model that we kind of studied a couple of years ago in the context of the factorization problem in low-dimensional gravity. So, you will see how it connects with symmetries and lack of symmetries in gravity. So, in recent years, when we did the paper, so maybe 5 years ago now, it became understood or known that in low-dimensional gravity theories, at least the theories which you define with the Lagrangian, there is an interesting paradigm or feature that Euclidean wormholes are present, and they imply that the partition function of the theory with disconnected boundary does not factorize. And there has been a lot of literature on this topic, and by now I think, I wouldn't say it's settled, but it reached like a steady state in some sense. And this property was originally interpreted as the fact that the usual holographic duality should be interpreted as a duality between a gravity theory and an ensemble of CFTs of some type. And this also had important consequences for understanding the information paradox in these lower dimensional quantum gravity theories. And my talk is about just prehistoric toy model for this mechanism, which we can kind of solve. And it starts from the most well-known type of holographic duality, holographic in quotes, which is the duality between a Chern-Simons theory in the bulk, so like a TQFT, and this ensemble of, I will explain, and rational conformal field theory. Of course, Chern-Simons theory is not a theory of gravity, so it's to make sense of this, we have to add to the left-hand side some over bulk geometries as to implement some kind of gravitational path integral. And this kind of construction was done by Maloney and Witten in older years, and recently by studying the Narayan ensemble of CFT, so free bosons, certain number of free bosons, and then this was also exploited in many follow-up works. Okay, so this toy theory, since you have Chern-Simons in the bulk, has this, we'll see we have this kind of factorization problem, but it also has another problem that it has global symmetries. So Chern-Simons theory has topological lines, and this violates the usual idea that global symmetry should be absent in a theory of quantum gravity, no? In the generalized sense, so here we'll talk about one-form symmetries.
Just a small comment. You're not the first person to do this, but it's because of how it appears on Inspire. Irene Valenzuela is also an author of that paper.
Oh,
she's V, so it's et al.
Ah, okay. then I apologize to it because I looked it on Inspire. I went, okay, thanks. Okay, and we will just make an observation and explain that both problems can be solved in this toy model if we insert if we modify the prescription for the path integral of the bulk by some generalized gauging, which is a mesh of topological lines. And there is a dual description of this generalized gauging, which is the insertions of, not here. Well, this will remove this symmetry because we gauge it, and we will see that it also will factorize wormholes. So the wormholes will be just equal to the partition function on disconnected boundaries. And there's also a nice alternative perspective, which in our paper we didn't really pursue, which is that this generalized gauging can also be thought as the insertion in the path integral of some end-of-the-world branes, which open up the wormholes. Of course, the theory is topological, so these are topological end-of-the-world branes, which are usually called gapped boundary conditions. And this is like the cartoon of the of the solution. And a similar mechanism was also proposed for JT gravity by various authors. And in this case, these are, yes?
Yeah, so I'm sure you'll discuss this later. But generally, if we gauge a discrete global symmetry, we will get some global symmetry back.
Yeah, absolutely. So
we still have some global symmetry to deal with later.
It's just that in this case it will not act on anything, so it will be like a trivial symmetry. The one that you have in the beginning has charged objects, which are the Wilson lines. If you gauge it, in the case of the Chern-Simons theory, there is no local operator that is charged under dual symmetry. So for all purposes, it's not there.
But are there non-local operators that are charged under this symmetry?
Not that I know of. But yeah, but I agree. I agree with your point. Like it's correct. It's just that in this particular case, it works in this way. Of course, usually you gauge continuous symmetries. Then in that case, it's more subtle, no?
Right, but this here is discrete.
Yeah, absolutely. So that's the point that makes it work is that you don't have operators charged under this dual symmetry. I mean,
is there something straightforward to verify?
Yeah, like the TQFT that you have after gauging is a trivial TQFT, and it is an SPT. So that's the point. Okay, but thanks for the question. And people also expect, if you believe in string theory, that if you really UV complete the theory, you shouldn't have this kind of problems, and the RCFT should be like holographic duality should be an exact statement. And in some settings, there's complicated computation that show that this factorization actually happened. But it's not a settled story as far as I'm concerned, but there is reason to believe that this is correct. Okay, so let's go on. So just to do some basic dictionary about how Chern-Simons theory and RCFT are related, and basic dictionary between the two, which will be useful for the rest of the talk. So we'll just consider G-level K Chern-Simons theory. So there is a gauge field, a G gauge field A at some level, and you have this bulk action. This has been, of course, studied many years ago. So I'm just gonna give you some small synopsis. So this is a topological theory on closed manifolds. And it has interesting topological operators, which are lines in some integral representation of G-level K. But importantly, on open manifold, the story is different because we cannot have topological boundary conditions in general. And the most we can do for a generic theory is to have holomorphic boundary conditions. So this also requires some counter term on the boundary, which I will not talk about. So we have this theory which only depends on the complex structure of the manifold. And you can do the same for generic 2+1D TQFTs. There are some kind of free boundary conditions that you can choose. And they are the equivalent, as far as I'm concerned, of this holomorphic. They will not be holomorphic in general, but if you have a more general TQFT, there is something which replaces this, which is not topological. And this is the best you can do in general. Okay, so just...
Can I ask a question?
Yeah.
I understand you're using this as a toy model, but this is not really a holographic, it's not even a duality, right? This is...
No, this is like even the pre-toy model. This is not even a toy model. This is just...
yeah, okay, just because you said duality between...
Yeah, because this will be chiral theory, so there is no notion of having a CFT there.
My point is that it's not a duality because in this case it's bulk degrees of freedom coupled to boundary degrees of freedom, not bulk degrees of freedom equal to boundary degrees of freedom. This is very clear, for example, if you have a lattice model realization.
I think it's the same as the usual thing. This is just Chern-Simons theory with some boundary condition. There are degrees of freedom of the boundary which come from the bulk.
And there are also bulk degrees of freedom. For example, if the bulk has a non-trivial handle.
Yeah, that's the point why the duality should be with an ensemble, not with a single theory. So the bulk Hilbert space has a finite dimension, and that finite dimensionality shows up in the fact that you cannot have a good duality. So the bulk Hilbert space on closed manifold is not one-dimensional, and that gives you the ensemble in some sense.
Maybe we can discuss more.
Yeah, but I think this is a good example of duality, but the problem is that there is no sum over geometries. Like, this is not a gravity theory. Okay, but just to give a dictionary, if you compute things in the Chern-Simons theory, you will find essentially conformal blocks of the chiral algebra. So, for example, if you take a solid torus, this is a field in, and you put a line lambda, then it computes a character for the chiral algebra. This we will need afterwards. And if you make lines end on the boundary, like this on the sphere, it computes some conformal blocks. So that's kind of the basic dictionary. That's all I will need in the talk. There are many more things, but I don't want to go into too much detail. And my interpretation is that these objects are not really physical because they're not invariant under large diffeomorphism at the boundary. So they're not modular invariant. Of course, the character is not modular invariant. This is not modular invariant. While a physical object, like a partition function of a physical theory, is modular invariant. You can make this better if you like sum over modular images, and then the answer, if it's not zero, is modular invariant, and that's what has been done in the literature. Okay, that you should think about as the toy model. Okay, and okay, this theory also has some kind of formal, so you can consider theory on manifolds which have more than one boundary, and of course the answer does not factorize. It's easy to see. So, for example, this I drew like the T2 times the interval wormhole, so this is just interpolating T2, and what you do is just that you cut here and you insert the complete basis of states, and what you do is essentially you cap off a cycle of the torus on both sides, and you just insert a line that's the basis of state. So you compute these characters, but it's the same. No, you have a sum of the states, and then you have the chiral and anti-chiral part, which is not the product of two things, clearly, no? And this similar computation was done by Kotler and Jensen for the ADS3. And the same happens, just that this lambda becomes some principal series label of SL2R. So there is some problem, clearly. The answer does not factorize, and the symmetry is present in the bulk. So, and in some sense, my way of thinking about this is that the Hilbert space in the bulk is not one-dimensional. That's what eventually drives the problem, as has been pointed out in various papers. So let us now review how you actually describe a physical theory using Chern-Simons theory. So like a modular invariant CFT. This is all well-known stuff, so I'm just reviewing it so everyone can follow. And this has been, I think the first paper when this was pointed out is quite old paper by Moore and Seiberg, and then there was some paper in the 2000 by Fuchs, Runkel and Schweigert, and like a long series, and then some papers by Capuzzi and Saulin, and then much more recent literature. So in this case you have to consider some non-chiral TQFT, because of course if you have the chiral central charge, you cannot have a modular invariant answer. So so for example, GK times G minus K Chern-Simons. And what is a physical theory? For example, on the torus, you need some sum of characters with some matrix here, which is modular invariant, no? And the way you define the character now is the solid torus partition function inserting a line A. So if you are in this example, A is just some label of GK times some label in G minus K, no? And then you have to take some linear combination, and this is just a partition function of the CFT, no? And this is, the old literature is called the mass matrix. And if you want, this result can be interpreted as inserting in the bulk here, instead of this small a, curly a, which is this linear combination here. And this you should think as an object in the bulk theory. There is a topological line, a special one though. But you have more constraints. Of course, this was just the partition function, but this doesn't define a CFT. So to define a CFT, you also need to consider correlation function. And so if you consider 3-point function and 4-point functions, you get the following constraints. So this is just the fact that the 3-point function is single valued, so you can bring this operator around the other. And then you consider crossing symmetries of a 4-point function, and some other equations that you can derive similarly. And this defines some special junction between this curly A that you will also need. And together with modular invariance and these conditions, this will describe something that is called the commutative Lagrangian algebra. this is just, so the definition of the Lagrangian algebra is just these conditions here, but without the sphere around. So the sphere just is needed to connect with CFT. No? So this would be a 3-point function of a CFT, like a compact boson. This would be a 4-point function, and these conditions tell you that this behave like a physical theory. So they will be crossing symmetric. They will not have monotomies, etc., etc. And this just tells you the spins are integers. So the dictionary now is that to have a physical CFT, you need a TQFT plus a specification of this object here, A, together with this map. This we call Lagrangian algebra, okay? Good, and this was pointed out in the papers earlier and in various work by Kong and Capuzzi and Saulina in a different context. So this came out in very different contexts and, of course, across the years. So, and if you want the dictionary now is that this Lagrangian algebra, so these choices of objects, are just the physical CFTs which share the same chiral algebra. So they're just related by some Olby folding. That's the basic idea.
Sorry, but lost.
Yeah.
Do you take the bulk theory to be the original transassignment theory, or transassignments times is time reversal?
Time reversal. That should be the example. Otherwise, you don't have Lagrangian algebras. No, that's the point. Yeah, but it might be that there is no Chern-Simons description. Maybe some is some coset. No, so you okay. So, but yeah, the example you should keep in mind is just Chern-Simons times the time reversal. Okay. Good. And in recent years, there is like a lot of work in the context of symmetry TFT to make this more general in some sense. This is like a proto example of symmetry TFT by various groups, various people, and so it ties up with all this stuff. So if people know symmetry TFT, they know this stuff. It's obvious, but they just presented it in a rather different manner. Okay. And okay, the simplest example is just U1 as a free boson. So you take 2 U1 level k, level minus k, and you have the lines are the following. And these are the Lagrangian algebra. So when you have a number omega which squares to 1 mod 2k, this is for bosonic stuff, then this guy will be Lagrangian algebra. And you can check, for example, the spins are integers very easily, and these are just all defaults of the compact boson which preserve the chiral algebra. So you just mod some zk. It's not particularly illuminating, but it's the simplest example. And of course, these are classified, all these kind of all defaults. So you can check that it's the same as the classification. You can do it for many bosons and so on. And yeah, there's also some more recent work in which this kind of ensemble average over like rational bosons can be thought about averaging over quantum codes. So it's just a different reformulation of the same mathematics, as far as I'm concerned, but there's also this different body of work. But for non-abelian theories, of course,
so is the ensemble average over all Lorraine or just rational torus models?
In our
What's the ensemble? The ensemble average.
I mean, our models is just rational radii, but you can do the irrational like Narain if you consider R to the D Chern-Simons instead of U1 level k. It works the same, just the definition of Lagrangian algebra is slightly different, but you can show that you get the correspondence. In the paper, we put just the case of one boson, but I mean, we also had the computations for n bosons. They are the same, but we just didn't write them down. But of course, this is what you can do. But when you go to non-abelian, so not free bosons, the story is very complicated, and the classification of modular invariants, which is the same as classification of Lagrangian algebras, is a really hard problem, and it's solved for SU2 and SU3 as far as I know. So that's and of course, if you want to do real CFTs like irrational, then the relevant thing is something like SL2R maybe, or Virasoro, which is extremely more complicated. So that's really hard problem there. So this is like free model for the hard problem. So now let's just describe what is the description with gauging. So in practice, all these equations I gave you for the A allow to define some, you can think of them as the equation which tells you how you can gauge a generalized symmetry. And what you get after gauging is a TQFT whose total dimension is this, and if you use the condition of the Lagrangian algebra, is 1. So the bulk is trivial, there is only one state in the Hilbert space, and this state describes the physical CFT. Okay? And if you want to write down what is a single CFT partition function, you just insert a mesh of lines in a dual triangulation for the manifold with the boundary. So like this is genus 2. And so you put lines around all the cycles. This goes around the cycle like this. I couldn't draw it very well. And this you can show it computes the partition function of the theory. And the conditions that define A, so the ones I showed you before with three-point function and so on, assure you that this object is independent of the triangulation you choose, which is just a choice that you make. So you just invariance on the Buckner moves, which is what you want for gauging a symmetry. Okay, so let me also tell you a dual interpretation, which is this one with end of the word branes. So there is a nice mathematical isomorphism between these Lagrangian algebras, which I described before, and the topological boundary conditions for the TQFT. The map is very simple to describe via pictures. So one way to think about it is that you can just gauge the symmetry in null space. So here I have my theory, and here I gauge the symmetry A. I told you here is trivial, the theory has only one state, so you can think there is nothing. And the whole setup is topological, so this guy will be a boundary condition for the TQFT, but a topological one. And of course, every time I have something that, some Lagrangian algebra, I can do this, so the isomorphism is the following. And if you think of it gravitationally, these are end of the word branes. No, this is the gravitational spacetime, and this is how it terminates dynamically. And if you want to recover, so if you want to go back in the other direction, you can just consider the gap boundary condition on a cylinder, like this. Here there is nothing inside, and then you shrink it, you get a line operator, and it turns out it's just this A. So that's how you prove the isomorphism. Then you have to do some mathematical computation, but this is the picture of the isomorphism. And so then I just show you how you find factorization, which now is like a one life proof. So I tried to trivialize as much as I could all the reasoning. In the paper there is more formulas, but this is just for the talk. So let's try to consider this TQFT mod A on open manifold. So this part here is just nothing. So it's just a path integral, no? Describe some state. But the Hilbert space is one-dimensional, so the state you can think of it as starting for the boundary condition and time evolving in the future. That's the only state. You can represent it in other ways, but this is one representation of the state. And if you want to consider the path integral for the gauge theory on a connected boundary, so here now on these boundaries here, you have like holomorphic times antelomorphic boundary conditions. So I'm computing some CFT stuff here. Now I can perform surgery, so I can cut the geometry at this point and insert a complete set of states. But there is only one state, which is this one in the gauge theory, so I can just insert it here, 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 and then just the picture becomes this one. And every single of these guys is just a partition function of the CFT, so it's just the picture I had here. It's just this picture. I drew it in 2D because in 3D it was too hard for me to draw it. So this is what you get.
Can I ask, what are your rules for summing over topologies in the 3D theory? It seems like what you're saying is that in your 3D theory, you want you could call it ER equals APR. There's a gauge constraint that lets you just cut the wormhole into this as equal as configurations of the path integral with the other one. Yeah, so it looks like you have no degrees of freedom associated to the sum over topologies?
No, because in the bulk, essentially, after you have given the prescription of this Lagrangian algebra, the theory is trivial. So this geometry is gauge equivalent to this geometry, if you want. So the sum over topologies, there is no real sum of the topologies. You're just counting a thing many times, and you should just take it out as a gauge symmetry.
I'm confused. Are you telling me to get the factorization, you have to necessarily trivialize the theory in the bulk?
But you need that the bulk Hilbert space is one-dimensional.
Do we expect that to be always the case?
I think that's on closed manifolds, I think so. But in models, in models which do not have like the usual duality, it will not be one dimension. Then you will have some kind of ensemble. I think all the examples in the literature that work in this way, if you...
You mean factorization requires the Hilbert space to be one-dimensional in bulk?
Yeah, I think so.
Is that the statement?
Yeah, I think so. Just that sometimes it's hard to define what is the Hilbert space in the bulk. So, but okay, in these time models it's easier to see. But yeah, I think so. But I don't think it's a theorem. No, but I think this is what expected.
Well, is the question whether that's what we expect quantum gravity to be?
Yeah, exactly. So I think it's expected that you need this to be true. Okay, and this is just a very simple toy model in which you have a lot of control over the bulk Hilbert space, so you can understand what you need to do. And okay, so let me just make another comment. So this, the way I think about this was just a toy model, but the way I think about this is that you start with a theory which is not UV complete. This was just some low energy description of the that gives you some ensemble. But the UV completion has these heavy degrees of freedom, which are the branes. In this case, it's end of the word branes. And the UV completion should tell you that you have to insert this in the path integral. So here you have to do it a bit by hand. And in JT gravity, you can also show that this happens if we insert the right kind of branes. Now, coming to prospects, it would be nice to see whether there is some case in which you have a UV complete model that gives you some 3D bulk theory in which this actually happens. No, I don't know of any case in which you can do it explicitly. This would be very nice, and that would be how the problem gets solved. But I don't know how to do it, so it's a prospect for the future. And of course, another thing which is very nice to do is to connect this with pure ADS3 gravity. Or some people now call this Virasoro TQFT. Okay, that's a long story, but essentially the idea of treating 3D gravity is some topological field theory with some commas, so that you try to make sense of it. And this is...
Sorry, maybe I have a silly question. So, are you saying instead of trying to interpret the CFT as an ensemble, we should try to think about there is some branes in the bulk that cut the wormhole? I think the logic is reversed from the previous literature, right?
No, I would say that if you UV complete your theory, your bulk theory, then when you go to the effective description, if you are to have not an ensemble duality but a usual duality, then you would expect to have some kind of heavy degrees of freedom like these branes, which allow you to cut the wormholes. And so my prospect was just that it would be nice to have an example where this actually happens from the UV in some sense, that you can see it coming out.
Maybe one comment to that question is that I think you could view this as picking the data you have to specify to pick a member out of the ensemble.
Yeah, exactly. The brain picks a member in some sense. But the UV theory should tell you which is the member, no? But I don't know of any computation that is very sharp in this direction that really gives you or falsifies the idea, no? It's fine. So then the other comment is about this connection with pure ADS3 gravity and this Virasoro TQFT, which is what people are really interested about. So trying to understand what is the dual of pure gravity, if it makes sense. And this idea that 3D gravity is some kind of TQFT for a non-compact gauge group with some commas. And roughly speaking, at least this is kind of agreeable in some sense. Topological lines in the bulk describe representation of the Virasoro algebra with fixed central charge. So then there are some issues about the vacuum, for example, but for states above the Brechol threshold, I think this is kind of fine. And of course, if you put this just this consistency condition like that, you find the crossing symmetry and single valueness for the correlation function of irrational CFTs, which of course you don't know how to solve, which is because it's the same problem as classifying irrational CFTs. So progress in this sense is very hard. It would be nice to have some new idea coming in from TQFT, but people have tried for a long time, and it's really hard to have a sharp complete idea about this. I mean, you can do some progress if you study this non-aligned CFTs, so this out-to-reach and Simon theory in the bulk, which is much easier, and then you can do some nice description. But if you want some real CFT, which is not just free bosons or some other default thereof, then it's really hard. And I don't know of any like definitive progress in this sense. One thing I thought about when I was working on this is that maybe if one could look at the C's. Usually people look at large C because it's simplifying regime, but one could look at small c because in this case you know what are the members of the ensemble, just the minimal models, no? So you have a minimal models and orbifolds, but then the bulk is a bit harder. Like one should make some effort to understand what's going on in the bulk, but this should be a more treatable regime instead of a large C for this kind of question, at least.
I'm a little bit lost in the logic. So, what do you want to do with the topological lines in the Virasoro TQFT? Do you want to get rid of them? You want to gauge them?
I think you want to gauge them in some sense.
But after you gauge, presumably you are no longer working with the Virasoro.
No, then you get trivial TQFT, you get a member of the ensemble. I just want to know if using this idea I can find some information about the ensemble, or if I have a UV completion of this, which gives me the Virasoro TQFT at low energy, if I can have some way to detect which member of the ensemble I get. Or just, I mean, much more stupid, just to generalize a result to this non-rational case, but it's just very hard. So yes, so my only idea was just you could look at the smaller than one, which is a bit more understood, and see what happens in the bulk, so rephrase the things in the bulk language. But okay, it's not been done so far. And some nice similar construction also using this holomorphic boundary condition have been employed to describe Goldstone theories for generalized symmetries, so spontaneous symmetry breaking in some recent papers. So this is also like a nice kind of set of ideas that I think one could employ. And yeah, so this is what I prepared. It's a bit before, so thank you for your time.